Good morning. So, I want to talk today about a couple of things. There's one topic that we haven't covered that we need to, and that is uniform circular motion. So, when an object's moving in a circle, the velocity is changing constantly. Remember that acceleration is equal to dv dt. So this says that it's the rate of change of the velocity, and this velocity is a vector. So as an object's moving in a circle, that velocity is constantly changing. What we're going to talk about is an object moving in a circle with the magnitude of the velocity being constant and the direction of the velocity changing. Okay? So let's think about a circle. Looks more like an apple, but okay, here's an object moving in a circle of radius r. I'll just put a little point on here. I'm not worried about the mass right now. When we start talking about Newton's laws, we'll get to the point where we can deal with the forces acting on this object. So let's say that it's traveling clockwise in this direction. So here's the velocity vector at that point, and in some time delta t, the object is moved down here and the velocity vector is now at that point. We call this the tangential velocity. So this is how the object is moving tangentially as far as the velocity goes. Now, you can see that maybe the magnitude of these two vectors is the same, but the direction has changed. This produces an acceleration. That acceleration is toward, this would be A, I'm going to call it not A sub t, A sub c. This is called the centripetal acceleration. Okay? So it's pointing inward. The velocity vector is changing, and this centripetal acceleration that's on the object is pointing toward the center. That's what centripetal is. So I'll do a little quick explanation of this, or quick derivation of this uniform circular motion. So let's say that here's a little segment. This is the center of the circle. Here's a little segment of the circle. Call this V initial. And let's say it's moving like this, clockwise, like I have over there. And this is V final. It's moving this way. This is delta theta. Okay? So it's changing some angle around the circle, and in some time delta t, the velocity of the object went from here to here. So if we look at the angle between the velocity vectors, all right, so maybe this is V initial, and this is V final. Okay. This would also be the angle delta theta. That's the angle between the initial velocity and the final velocity. Let this distance equal r. This is r, the radius of the circle is not changing. The object's moving in a nice, perfectly circular motion uniformly, meaning that the magnitude of the velocity is not changing. Then this would be, let me draw this. Let me call this r initial. So these are our position vectors. This is r initial and this is r final. Delta r is here. Okay, that's delta r. All right, that's from that initial position to the final position. This is delta v. I'm not going to draw it on here, but that's delta v. That's the difference between v final and v initial. Okay. There is a relationship due to this r initial, r final, and delta r, v initial, v final, and delta v. By similar triangles, you can write this down. Delta v divided by v is equal to delta r divided by r. Okay? So this is just the magnitude of the velocity. This would be the speed, or the change in speed. Well, that's not right. This would just be the magnitude of the change in velocity. This is the velocity v, that's the speed. This is the magnitude of the change in the position divided by the magnitude of r, which is just the length of that vector, okay? Now, I'm going to move this around. So delta v, do a little bit of algebra. Delta v is equal to delta r divided by r. So I'll just move v over here to the right-hand side, okay? Then divide through by delta t, because this did happen in some time delta t. So I'm going to divide both sides by, let me put it over here, by delta t. Okay. So now on the left-hand side, what do you have? You have delta v divided by delta t. That's the magnitude of the acceleration. That's on the left-hand side. Okay? This would be just the magnitude of the acceleration. Right? That's delta v divided by delta t. That is acceleration. Then on the right-hand side, you're left, well, I'm going to change this around a little bit. It's v divided by delta t times delta r divided by r. Okay? That's not what I want. This is what let me write, sorry. Let me rewrite, I'm not looking at my notes. Okay? This is v divided by r, that's what I want, and then delta, this is delta v, or delta r divided by delta t. Okay? So I have v over r, that's the velocity, or that's really the speed. It's the magnitude of the velocity. That's the radius of the circle. And what is delta r divided by delta v? Well, this thing is just equal to v. Okay? Delta r divided by delta t. So this is equal to v squared over r. that is that centripetal acceleration. That's the magnitude of the centripetal acceleration. Usually written as I'll usually write it like this. A centripetal is just v squared over r. Where this is, it's understood. Maybe I won't always write it down, but that's that magnitude of the tangential velocity. Okay? Now, for an object moving in a circle, okay, for an object moving in a circle of radius r, all right, the period is the time it takes for the object to make one revolution, okay? The period is equal to t. If you have a circle of radius r, however long it takes for it to make one revolution, it's moving in a circle, that's what we call t, big T. That's the period. What's the period of the moon? The moon orbits the Earth. Okay? So the distance around the circle, the circumference of the circle, is equal to 2 pi r. Yeah. Take a circle, go around, walk around in a circle. If you know the radius, it's 2 pi times the radius. That's the distance around the circle. So, what's the velocity of an object moving in a circle? Well, it's the distance divided by the time. So it's 2 pi r divided by t. So that would be, if you know the period of an object and you know the radius that it's moving in, okay, around that circle, then the velocity is equal, the magnitude of the velocity is the distance around divided by the time. We can move this around. The period is equal to 2 pi, either way, 2 pi r over v. So if you know the radius, you know the tangential velocity, then you can calculate the period of the object. Okay? So these are things that are on the equation sheet. That's stuff that you're going to need to know to work the problems. So let's look at a typical type problem based on this. Let's say that a small mass moves in a circle or moves on a circle of radius r equals 0.5 meters. The period of the motion is 0. Let me write it as t equals. T is equal to 0.5 seconds. What is the centripetal acceleration? Okay, this is dead simple. It's just plugging into that equation. You do have to do an intermediate calculation with the period, but to find v, but that's fairly trivial. So we know that the centripetal acceleration is v squared over r. We don't have v, but we have the period, and we have r. We can calculate v, because v is equal to 2 pi r over t. Okay? So let me go ahead and I'm going to get rid of this sort of blobby looking circle. So let me go ahead and calculate v. Once I have v, take the square and square v and divide by r. So v is equal to 2 pi times 0.5 meters divided by r, which is 0.5 seconds. Okay, I made this pretty simple. All right, so v is equal to 2 pi meters per second. So v is equal to 2 pi meters per second. That makes perfect sense. You got a radius of a half a meter, a period of a half a second. They cancel out. Okay. So I'll plug that in here and get rid of this. So A sub c is equal to v squared. So you get 2 pi squared divided by the radius, which was 0.5 meters. Okay. This is in, let me put the units in here. This is in meters per second squared. Okay, so this is equal to 4 pi squared divided by 0.5, and that has units of meters per second squared, and that's equal to 8 pi squared meters per second squared. And that's it. Okay. All right, so this is a typical kind of problem. You may be, maybe in the homework you're going to be given some sort of revolutions per second or something like that, and I can help you with that. But nevertheless, this is the idea. So an object that's moving in a circle is definitely accelerating. That velocity vector is changing as it moves around the circle. The magnitude of the velocity may be constant, but the direction of the velocity is changing. And you've all experienced this when you're riding in a car. You can be going at a constant speed, and if you go around a circle, in a circle, you feel that acceleration from going in a circle. Okay? It feels like something's pressing you up against, the side of the seat. You feel these forces that are based on these accelerations. I realize we haven't gotten to forces yet, but we will. Okay? So that's all I'm going to say about uniform circular motion right now. So I want to start talking about projectile motion. What is a projectile? Well, a projectile, when we start talking about a projectile, it means an object that is moving under the influence of the gravitational acceleration, and that's the only thing acting on the object. We're going to ignore air resistance. We're going to ignore any sort of interactions with other things. The only thing acting on the object is the acceleration due to gravity. Now, if I throw an object, I give it an initial velocity, okay? So let's say that here is the ground, and here is someone, maybe me, tossing a ball, all right? So I have a ball and I'm tossing it underhand, and once that ball leaves my hand, so it has some initial velocity in this direction, okay? Once that ball leaves my hand, it becomes a projectile. I'm not acting on it any longer. I've given it some initial velocity, leaves my hand, and it becomes a projectile. Okay? It makes a trajectory that is like something like this. Okay? And all along that path, the only thing that's acting on the object until it touches down or interacts with what we're assuming is until it interacts with the ground, okay, meaning it impacts the ground over here somewhere. The only thing acting on it is the acceleration due to gravity. And we already know that that acceleration due to gravity is in this direction, okay? It is vertical and it is pointed down, okay? So I claim, since space is divided into 3 independent dimensions, that whatever happens in the x direction, I guess for you guys, okay, the x direction does not affect that y direction. So whatever's going on in y does not affect x. What I'm saying is, once this object becomes a projectile, meaning it leaves my hand, that x velocity of the object, let me draw an exploded view here. Okay, here's the object. We break it into Vx and Vy. Okay, there was some V initial in the x direction, there was some V initial in the y direction. I'll make this Vy initial, Vx initial, okay? I claim that in the x direction, this component of the velocity will not change during the entire trip. It cannot change. There is no acceleration in the x direction. We're assuming that the acceleration due to gravity is perfectly vertical along this entire path. Okay? However, in this direction, the object is accelerating. It's experiencing an acceleration due to gravity along the y direction. So what happens in the y direction? It goes up, but it comes back down. Nothing happens in the x direction. It follows that initial velocity in the x direction along the entire path. Its final velocity in the x direction is the same as it started out with. Okay? Think about this. You are tossing a ball up and down. I thought I had some tennis balls in here somewhere. Oh, the wife probably threw them out. Okay, I'm tossing the marker up and down, up and down. Okay. That's our free fall, right? That's that y direction free fall that we had. Okay? Nothing strange about that. All right? Let's say now that I'm in it, so you're watching me toss this up and down. Let's say now that I'm in a car moving along. And I'm sitting in the car and I'm tossing this like this. I see the object move up and down, no problem. But what do you see? You see the object going like this. I'm moving, and as it goes, it's like this. Try this. As you walk along, you can walk and toss this object up in the air, okay? And it just looks like free fall. But what does your friend see? Your friend sees the object going, okay? What's happening in that x direction, if you're moving at a constant velocity in x, that velocity stays the same, and this velocity in the y direction depends on the acceleration due to gravity. Another example, sometimes called the drop ball, shot ball. Let's say as soon as let me change this up just a little bit. So here's the ground again. I'm going to have a little bigger person. All right. Here's a little larger stick figure. So let's say that we have an object and somehow I am able to throw that object with absolutely no initial velocity in the y direction. So I'm able to throw the object just perfectly with only the x direction velocity. What's the trajectory going to look like? Well, you all know what that's going to look like. It's going to come out fairly flat and then it hits the ground, something like that. I claim that if another object is dropped from the same height, and when I say dropped, I mean as soon as this object leaves my hand, back behind me somewhere, an object is dropped. So Vx initial is equal to Vy initial, and they're both equal to 0. So at the instant this leaves my hand, this object starts to fall. We all know what that looks like. That's just the object falling. I claim that these two objects will reach the ground at exactly the same time. No matter how hard I throw this object, that object and this purple object, they will hit the ground at the same time. Okay? That's the independence of the x and y coordinates. That initial velocity in the x direction had absolutely no effect on the y direction. Okay? This object will hit the ground at exactly the same time that this object hits the ground. I'll try to prove this to you. You can probably go on YouTube and search for drop ball, shot ball, something like that, physics. But I have a real nice demo. I hate to talk about these demos and then not be able to actually show them to you, but nevertheless, this is the case. So this is the idea of projectile motion. And what we want to do is, or one of the goals that we have is, by knowing the initial conditions for the projectile, where is it going to land? How is it going to interact with something else, okay, based on its motion in the x direction and the y direction. In the x direction, the only thing that we will have will be the starting position in the x direction, so some coordinates in the x direction, and we'll also have the velocity in the x direction, which will not change. In the y direction, it'll be the free fall equations. We'll have the coordinates in the y direction, the initial velocity in the y direction, and also we already know the acceleration in the y direction, which is g, that way. All right, so let me write down for projectile motion what these equations are. So we'll add a little bit of notation just to keep x and y separate. And the goal is to somehow, and I'll show you how to do this, the goal is to somehow figure out, based on what we know, well, do we solve for the time in the x direction and then use that for the y direction? Do we solve for the position in x and use that for y, or some such thing like that? And you'll see how this goes. So in the x direction, all right, Vx initial is equal to Vx final. Okay? That's basically it. Whatever initial velocity you have in the x direction, that does not change. There's no acceleration in the x direction. The velocity cannot change. I know it looks like from those parabolic trajectories, you really, really want it to change, but it doesn't. So this leads us to x final is equal to x initial plus Vx initial t. That's it. That's that just rate times time. We know the initial velocity. We know the initial position. We can find the final position, okay? In the y direction. In the y direction, it's just those free fall equations that we've already dealt with. So in the y direction, we have that y final is equal to y initial plus Vy initial t minus g over 2 t squared. That's that position time equation. You also have that Vy final is equal to Vy initial minus gt. That's the equation that relates that acceleration due to gravity with the velocity, okay? Also, you may be able to use that Vy final squared minus Vy initial squared is equal to minus 2g y final minus y initial. We had all these. These are those free fall equations, okay? So this is the one that deals with acceleration. This is the acceleration, initial velocity, position equation, all right? And by knowing something about the trajectory of the object, maybe its initial velocity and where it landed, we're going to be able to figure out different things about that path that the object took. Maybe in some case, we know something about the object just as it impacted the ground, and we want to find out where it came from. Okay, these are ballistics problems. All right. So let's look at a fairly simple example. I think I have one over here somewhere. All right. So here's our here's a building. We went through this the other day. It's 50 meters, so it's about what? 15 floors, 14, 15, 16 floors, depending on the structure. So let's say that an object is launched from the top of the building somehow, and this angle is 30 degrees, and I don't have enough room. V initial is equal to 10 meters per second, okay? So this is an initial velocity that's 10 meters per second, and it's at an angle of 30 degrees above the horizontal. So a fairly, shallow angle, 30 degrees above the horizontal. Here's the question. What is x final? What is xf? So I want to know, based on this trajectory, if this is 0, this is x initial is equal to 0, where does it land? Okay? What is V final? Meaning, just as it impacts the ground, just the instant before it impacts the ground, what's the final velocity? Okay? The first thing that we're going to do is we're going to break that initial velocity into components. You're always going to have to, I'm going to write this in general. This is V initial. This is Vy initial. This is Vx initial. Okay? Those will be the components of the initial velocity. Vy initial, this is theta. Let's do Vx initial. Vx initial is equal to V initial magnitude cosine theta. Just like always. Vy initial is equal to V initial sine theta. This one you have to be careful with. Why? Because if I were launching this below the horizontal, then this would be negative. Remember, you got to keep up with these SIGNs. If you have a negative initial velocity, meaning in the y direction or in the x direction, you got to put that into the equations. All right? If it's launched this way, that's a very different trajectory than being launched up here or being launched here. Okay? So I'm going to calculate these for this particular example. So Vx initial is equal to 10 meters per second, cosine 30 degrees. Vy initial is equal to 10 meters per second, sine 30 degrees. Okay. So Vx initial is equal to what? I don't have that. Yeah, I do, somewhere. That's 8.66 meters per second. Vy initial is equal to 5 meters per second. Sine of 30 is 0.5. So, okay. So what do I need to do first? Well, I'm asking you for the final position in x. So in the x direction, I'm going to get rid of this. So for x direction, which I just wrote down 5 seconds ago, x final is equal to x initial plus Vx initial t. Well, I have a problem because I don't know the time of flight. I don't know the time of the trajectory. However, we can figure out that time by using the y direction, because in the y direction, it's just free fall. Once that projectile leaves the top of the building, in the y direction, it's just going up and coming back down. Okay? I know the initial y velocity. I know the initial position in y, the final position in y. You can figure out the time for the time that it takes for it to impact the ground. So for the y direction, I'm going to use y final is equal to y initial plus vy initial t minus g over 2 t squared. Okay, I know this, I know this, I know this, I know that for sure. I can figure out the time that it takes for the object to make that trajectory. So let's do that. I'll plug in the numbers. Y initial is equal to 50 meters. That's the top of the building. Y final is equal to 0. Vy initial, I have it written down here, but I'm going to rewrite it, is 5 meters per second. Okay? Plug it in, solve. So, y final, 0, is equal to y initial, 50 meters, plus Vy initial t, 5 meters per second t, minus 9.8 meters per second squared over 2 t squared. Okay. Now we can solve for t. And you can do it with your calculator. You can do it with quadratic formula. Here, you can check me on this. The answers that I got are t is equal to 3.745 seconds, and t is equal to negative 2.725 seconds. Okay? This answer makes no sense for us. All right, we're not talking about in previous times like the object came from the ground and went up to the starting point or something weird like that. Okay, so this is no good. So t is equal to 3.745 seconds. That's the time it took the object to leave the top of the building and impact the ground. Strictly based on the y direction. Once you have this time, now you can figure out what's happening in the x direction. Okay? We know Vx initial. We know x initial. I made that 0, right? We can find x final. Let's do that. So x final is equal to x initial, which is 0, plus 8.66 meters per second. We figured that out earlier. That's Vx initial multiplied by the time of flight. 3.745 seconds. And I get an answer of 32.43 meters. So that's how far from the base of the building that the object would impact the ground. About 30 meters. All right, goes up, 30 meters from the base of the building. Okay? The next question was, what is V final? So let me draw a little aside over here. Here comes the object. It's impacting the ground. It's impacting the ground, and this is V final. Okay, so I'm talking about that instant right before it hits the ground. Well, we can calculate the final velocity in the x direction. We can calculate the final velocity in the y direction. Once we have that, we can calculate V final. X direction is dead simple. Vx initial is equal to Vx final, and that's equal to 8.66 meters per second. That x velocity did not change. There was no acceleration in the x direction, so the x velocity remained constant. What about the y direction? For the y direction, we know that Vy final is equal to Vy initial minus GT. Well, I have Vy initial, I know G, I know T, I can figure out Vy final. This is equal to 5 meters per second. That was Vy initial minus 9.8 meters per second squared times 3.745 seconds. Okay? So let me see what I get for Vy final. Negative 31.7 meters per second. That negative needs to be there. That tells me that that final velocity is in the negative y direction. During the beginning of the trajectory, if we were to calculate the y velocity, it would be positive, positive, positive. It reaches that peak. Then the velocity is negative, 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 getting larger and larger and larger in the sense of the negative direction. Okay? So if I were to write this velocity, this final velocity, in component form, V final is equal to 8.66 meters per second I hat minus 31.7 meters per second J hat. That's the final velocity in component form. It has a magnitude of 8.66 in the x direction and a magnitude of 31.7 meters per second in the negative y direction. I want to put this in polar form to get an idea of the angle at which it impacts the ground and the magnitude of the velocity. So V final, and if I write V final without the little hat, that's a magnitude, is equal to 8.66 squared plus 31.7 squared, and that's in meters per second. And this is equal to 32.86 meters per second. Okay? So that's the speed with which it impacts the ground, 32.86 meters per second. What about the angle? Well, the angle, I'm going to draw this. For the angle, you've got a big negative component and a small x component. This is 8.66, and this is negative 31.7. And these are meters per second, okay? Meters per second. All right. So I'm going to find the angle. So here I go on my method. You do it your way. I'm going to find the angle below the horizontal. So it's something like this. I'm going to find this angle, theta. Okay, that's the resultant. That's 32.86 meters per second. And I'm going to find this angle. All right. So that angle is theta is equal to the inverse tangent of 31.7 divided by 8.66, because if I think of moving this down here, all right, Yeah. Is that right? Yeah. Then that would be opposite over adjacent for that angle. So this is equal to 74.7 degrees. Theta is equal to 74.7. Now, there's a couple of ways you could report this. V final is equal to 32.86 meters per second at 74.7 degrees below the horizontal. Okay? Another way, that is a vector. It has a magnitude and a direction. Another way is, it's just another way of writing it. It's not a... V final is equal to 32.86 meters per second at negative 74.7 degrees. Okay. That would tell me, okay, you know that it's below the horizontal. If that was the x-axis, it's that way. Okay. This is the idea. You have those equations in the x direction, those free fall equations in the y direction, and you have to figure out from the information that's given, do I solve the x direction first? Do I solve the y direction first? Okay, and then by solving one of those directions first, you can use that information to solve what you need in the y or x direction. Think about this, like on this problem we just did. If you were given that distance that the object impacted the ground, okay, you could have used the x direction to figure out the time. All right? Then maybe using that time, you could have figured out the height of the building. Okay, this is the idea. We'll do several more of these type examples as we go along. Okay, so that's going to be it for today, and I'll be available this afternoon. I'll send you, if you're watching this, I'll send you an email explaining, but I'll be available, for emails and texts and so forth. So, okay, thanks a lot. Keep working on the homework. I'll post the homework for chapter 4. That's the stuff with projectile motion. I'll post that, and I'll see you guys tomorrow.